Thank you, everyone, for giving me this opportunity to present my PhD work in this competition. My name is Gour Govind. I have completed my PhD at University of Oxford. Today, my PhD title is going to be an investigation on strain localization in titanium alloys under different strain rates, where we studied influence of pre-strain, anisotropy, and stress state. This work was supervised by Dr. Antonio Pellegrino and co-supervised by Nick Petrinich. In my studies, I dedicated my time to study about titanium alloys, which has a wide applications for being a lightweight, coupled with high strength, excellent corrosion resistance, makes them suitable for space explorations, manufacturing in aviation sectors, and also in automotive industry as well, in defense sector. Their applications are also extended for manufacturing sports gear, biomedical applications such as like hip joints, and there's many more to list about titanium alloys. However, these wide applications requires a detailed understanding of their mechanical response, such as are they rate sensitive. So if you look at this graph, which is where we are trying to compare the high rate to the quasi-static, we can clearly see that they are rate sensitive. Also, they have like an effect coming from their manufacturing routes, such as like developing the texture effects. Yes, they do have a texture effect as well. That's what makes them very interesting alloys to study and save time for applications. In my study, in my thesis, the first contribution I did by developing the novel polynomial correction accounting for adiabatic heating and triaxiality. Why it was important? For that, let's look at this particular example where we try to study the dynamic strain localization. So the strain becomes localized at the high strain rate conditions when it's no longer homogeneous across the gauge length. If you look at this one particular example on your left, and once this non-homogeneity starts occurring in the gauge length, it affects an overall estimation of stresses, such as like if there is a uniform elongation, our true stresses are equal to the equivalent stresses. But once the necking initiates, the strain localization initiates, we see the contribution coming from other stress components, such as like radial and tangential, radial or hoop stresses. These stresses can still be corrected. True stresses still can be corrected for equivalent by using correction methods such as like Brigman, which is geometry dependent and requires continuous measurement of current radius and also the radius of curvature. However, now the question arises to us, does this correction factor account for adiabatic heating as well? Also, does strain history and strain rate affect the strain stress state in the necking cross section? That's where I organize an extended campaign where I try to study the effect of adiabatic heating on a dynamic strain localization, where I use the dogbone specimen and use Zwick tensile hydraulic machine to pre-strain 3 different pre-strain levels, 6, 10, and 14. Later, I use these pre-strain samples along with the pristine samples and tested by using the split Hopkinson tensile bar, which has two cameras. One is high-speed camera to observe the necking evolution. Second is infrared camera to observe the temperature evolution. Let's look at the one small finding from this testing campaign. If you look at this temperature evolution, where we try to compare the monotonic pristine and the pre-strain cases, we can clearly see that imposed pre-strain level does affect the failure strain of the alloy. At the same time, when we try to test the pre-strained sample at the high rate condition, initial phase shows almost a constant diameter evolution, which clearly indicating the huge role played by the adiabatic heating in these alloys. This whole setup also enables us to synchronize and in the same time to evaluate how the temperature is evolving as the necking is evolving. By seeing this particular example, you can clearly see as the necking is progressing, the temperature is also increasing. And it enabled us to quantify the temperature in all 3 to 4 conditions, which gives us the strong confidence about that how this adiabatic heating is influencing the stress state conditions in characterizing the material, which conclusively told us that temperature rise is inversely proportional to level of pre-strain. Now, this whole experimental setup allows us to measure the average stresses, but it doesn't allow us to measure all the stresses components such as radial and hoop, and therefore I did also numerical modeling by simplifying the overall geometry to the dogbone specimen, and then use the LS optimization tool where I can combine pristine along with a different pre-strain label so that I conclusively can come up with the one set of parameters or Johnson Cook and predict the overall material behavior. And in the end, I managed to get good global predictions by comparing the experimental measurements. And also, more importantly, in our case, the local prediction also agree well with the experimental measurement in the form of diameter evolutions for all the cases. Once we have the confidence in our numerical model, I use this numerical model to explore the stress state in the necking cross-section. For example, I tried to plot here the axial stress distributions with respect to the normalized radial coordinates across the gauge section. If you look at it, that in this particular graph, you will see that as the pre-strain level increases, the stresses across the cross section becomes flatter, and it clearly indicating that how adiabatic heating in monotonic cases is affecting overall stress evolution. To further elaborate, if we try to compare all three stress components, such as like axial stress, von Mises, and true stresses, we find that there is a large difference between the von Mises and true stresses in monotonic cases compared to the pre-strain 14% of samples. This gives us a great confidence that adiabatic heating is playing a huge role in defining the stress states in material. So now my task was to compare with other triaxiality corrections, which can be used to correct these true stresses for equivalent. For that, I try to compare the pigment, which is based on the volume conservations in the plastic regime and requires current radius and the necking curvature profile. I also use the MLR third order polynomial, which is developed based on the true necking strain and the true current equivalent strain. I also try to use the Gromada, which is semi-analytical formulations, to predict again these corrections. And when I tried to compare for the quasi-static response, I found quite reasonable good results. However, when I tried for the high rate conditions, it diverged quite drastically. That gave me motivation to pick either of them and try to modify it. For my study, I use MLR formulations and I modified it by adding an exponential term to account for the heat generation in the form of Taylor-Cooney coefficients and specific heat, along with the density of material which are under investigation. And I managed to put all the experimental measurements which I did with my infrared thermal camera. And when I tried to use this modified and dynamic LMLR equation, and I found quite reasonably good results, not just only for TI64, but also TI3AL 2.54V or the wide range of strain rate as well. So overall, the relative error for the proposed correction is below 3% in all the examined cases, with the maximum error equal up to the 2.51. And this modified correction is applicable for all titanium alloys. In the second part of my thesis, I tried to study the combined tension torsion effect on titanium alloys. So if we try to look at this, the numerical simulations where the compressor blade is interacting with the containment, we take this part and we try to plot the stress history. Then we see that stresses around these regions are far from being uniaxial tension or uniaxial compression. They are much more into combination of both, which gives us the clear indication that in the real impact scenario, the stresses are a combination of normal, shear, and failure. Therefore, it gives us the motivation to develop and appart the system to better understanding of material at failure so that we can optimize new component design while reducing their weight, also maintaining their mechanical integrity. Also, most of the material models so far are built by using the individual tension, compression, and the shear test at the wide strain rates. And current applicability of these methods are limited by experience and, of course, the validation cases as well. So for that kind of a test, for this tension torsion testing, I used tension torsion split Hopkinson bar, which was developed in our lab in the last 3 years. Based on the energy storage and release system, it is equipped with decoupled two devices. One is linear actuator, which is used to apply the tension, and another one is harmonic drive to apply the torsion. And it is also equipped with the jaw-shaped clamp, which basically helps to hold the incident bar along with the stored energy as well. And then we also use multiple camera setups since we were using wide range of the specimens such as like tubular and ligament specimen. For this particular study, we needed multiple cameras in order to observe if there is any failure occurring any side of the specimen. And for this particular study, I use very specific design, which is the four ligament circumferentially placed with a 1 mm gauge length of 1.5 mm of width. And for combined loading conditions, I use the ratio between the normal stresses and the shear stresses to define the range and the domination of the loading, either it's a tension dominated or shear dominated. Now, let's look at one of the representative example of conducted by using this machine. So if you look at this, this is basically trying to give us the information about the arrival of the input longitudinal wave and the input shear wave. And why it is important? Because both the waves travel at a different velocity. Therefore, it is quite important that both the waves should arrive more or less in the same time at the interface of the specimen, so that specimen can experience the combined loading effect. And as you can see, the arrival of both the waves is somewhere like under 20 microsecond, which is quite acceptable. Second part to observe is the achievement of the dynamic equilibrium. After initial oscillations, we can clearly see the superimposition of the input and the output longitudinal wave, which gives a clear confidence that the whole device is a strain control. And this is one of the representative engineering strain curve we achieved by using these experiments for the combined loading, and it clearly indicates that it's a tension dominated curve. It's tension dominated experiments. Now let's look at like one of the testing video. We can see that two different cameras are looking to the ligament, and it can see that it has a combination of not just the tension, but also there is a torsion is playing a role in this experiments. And these real-time images are further used for digital image correlations in order to identify the magnitude of these contributions in the form of engineering strain and also shear angle developed on the deformation history, and along with the combined effect as well. And all these testings, in the case of the pure shear, pure tension, and combined, are important to construct this failure envelope, which is shown here, which is placed where you can see the pure shear tests are conducted, are plotted in this direction, the pure tension are plotted here, and the combined loading is here. And as you can clearly see that as the strain rate is increasing, there is an expansion of the curve, also indicating the failure behavior is changing. And for this, I also use Drucker-Prager pressure criterion, which also help me to understand the failure boundaries and the rate sensitivity of the material I'm testing at the different conditions at the different loading angle. I also took these samples for the various loading conditions, and I tried to compare that if I can observe some features which is indicating about the combined loading conditions. So for instance, if we try to see it just like for combined loading conditions, we do see the elongated dimples and the tear dimples, which is clearly indicating the domination of the shear stress, also along with the void formations and the deeper dimples as well. This particular method I extended to construct the failure locus for multiple titanium alloys, which are reported first time in the literature. And in my final section of the thesis, I also worked on the experiment method to measure the elliptic necking cross section. For that, I used the twin camera setup employed on the split Hopkinson bar. And as you can see that both the cameras are giving the different diameter evolution, clearly indicating the anisotropy exists in the material. And based on these two, we get two largely different two stresses to strain. And if you try to measure the cross section as well, we see the quite beautiful ellipticities indicating about the anisotropy. Therefore, I adopted a method which was proposed for the quasi-static condition in literature, which requires two camera along with the distance is known, diameter is known to you as well, help you to measure the anisotropy angle. And based on this information, I can measure the semi-minor and semi-major axis of the ellipse, helps me to estimate the area and gives me the correct true response. I repeated this test for the commercially pure titanium grade 2, which indicated quite high anisotropy, and it produced quite consistent result. This also has been successfully implemented for the additively manufacturing titanium alloys for various orientations. And that brings me to conclude my work, where I just reported that I worked on improving the triaxiality corrections, which is applicable for ductile titanium alloys and helps to account the adiabatic heating and high strain rate. I also developed the experimental methodology for anisotropic necking and multi-axial failure envelopes. In the future, I'm also working in extending this modified MLR for anisotropic necking, and at the same time development of the numerical modeling numerical modeling of ligament type specimen for the better insight to evaluate this test state under loading condition. Thank you. These are the publications with this work. Thank you very much.